Okay, so real quick, I'm going to take roll. So while I'm taking roll, why don't you guys look at this one here, please? Think about how you could find the real zeros. Okay, what do we do? What do we do here? Yeah, now we'll probably let's think about this strategically. What's probably the first thing we would maybe try to do? Yeah, we got 4 terms, so we'd see if grouping would work. Is it going to work? No. It's not going to work, is it? You can tell it's not going to work because you can always kind of look and see, is the ratio of, this divided by this, or first divided by second, or second divided by first, can be equal to the corresponding ratio with 3 and 4, terms 3 and 4, right? It's not going to work, is it? If I factor out a greatest common factor here, I can see that there's no way I'm going to get that same leftover, right? So that would have been the easiest way to go if it worked, but it didn't. So then now we've just got to try, what's the theorem called? The what? Unknown theorem of algebra? No. What is it?
Rational root theorem.
Rational root theorem. Yeah, we got to try the rational root theorem. So we're going to try to find any rational zeros, right? They'd have to be, how would we build the rational zeros, the possible rational zeros? What would the numerator have to be?
Factors of constant.
Factors of the constant, so factors of 15, and the denominator would be factors of?
Leading coefficient.
Yeah, leading coefficient, which is 1. Right, so we'll just make our list, and let's kind of go through up, and let's practice that little template that I showed you guys yesterday, or was it the day before? I can't remember. Sunday? Was it Sunday? Were you here Sunday? Yeah. So let's go through. We're going to find what are our factors of 15, plus or minus 1, plus or minus 3. And we'll start with the easiest ones and work our way up, right? Okay, so we'll make our little template here. We'll put the coefficients out. What are those going to be? 1.
Negative
1. Okay, and then we'll just, now each line will correspond to a test value, right? So let's try 1. And then remember what we're going to do is we're going to do all the operations at once. And so what we're going to populate this row with would be the numbers that would have shown up below the bar in synthetic division, right? So what goes here? 1. We bring the 1 down. Now what? 1 times 1 is 1. Plus 1, right? We're just going to go ahead and do it all at once. Plus 1 is 2. 2 times 1 is 2, plus negative 17 is 1 times negative 15 is plus 15.
0.
So we got it. We got lucky, got it on the first try. Right, so 1 was successful. Now, do we have to go any further? It's quadratic, right? If we're just trying to find the zeros, and we're trying to find the real zeros, right? So that's, if they're imaginary, we don't have to mess with them this time. What does this correspond to in terms of a quadratic factor? Okay, good. So then we've got, this corresponds to x squared plus 2x minus 15. And we don't have to write this there, but 1 was a successful 0, and so that would have been the factor what? X minus 1. We don't need to write that though, right? Because we already have that 0. So now we know that this one gave us x equals 1. When we set this whole thing equal to 0. Now we just need to find the zeros of the quadratic factor. So what are our options? Magic numbers or quadratic formula. Or I guess we could complete the square, but we haven't done that in a while. Yeah, so we get x plus 5, x minus 3. So what are our zeros? Equals positive 3 right there. So 1, negative 5, and 3 are our answers. Make sense? Okay? All right. Questions on that? Does that make sense? Any questions?
I got a question.
Yes.
So, you factored out the 1 or whatever?
We factored out the 1. Mm-hmm.
Yeah. How does negative 7? Yeah.
So are you wondering, the question I bet is, on this row right here, what is this row?
How did you get x squared plus 2x minus 1?
Okay, good, because these are the, remember that this is the bottom row. This is what would appear normally when we did kind of synthetic division the longer way, right? We're just trying to do a real abbreviated way so we can check all these numbers and not take up too much space, right? Normally, this would have been the stuff that would have shown up. Like, here's our coefficients. There's our remainder box. That's the 0, 1, 2, negative 15. Remember what those mean. The numbers in front of the remainder box are in, if you're moving to the left, in increasing order, those are the coefficients, right? So that's always going to be the constant. Scoot over to the left 1, it's the coefficient of x squared, x cubed, x to the 4th, if they were there. Okay? All right, so let's try this guy. Same kind of thing. Only this time, what are we trying to do? Oh, real zeros, okay. So same kind of thing, right? What are our potential zeros going to be this time? We've got all the factors of what divided by the factors of what? 12 over 4, okay. So that gives us a lot, but we're just going to, because of time, I'm not going to give you really, really complicated ones to do here. They're going to, we'll try the integers first, and typically the integers are going to work. Right? So you're going to find at least one. So what are the integer coefficients of 12? Well, actually, let me take a copy of this first.
1, 2, 3, 4, 6.
So, yeah, we get what? Plus or minus 1, plus or minus 2, plus or minus what? 3?
4, 6, 12.
So that's a lot. I mean, we're going to hopefully find something. You can see why you want to be able to do this kind of abbreviated method here. So what are my coefficients?
1, 2, 4. 4.
Okay, and let's try 1 now, about. So what do I get here? 4. Now what? 35. Everybody see that? 4 plus 31 is 35. Okay, is this going to work? You can already see, how come this isn't going to work? Yeah, they're all positive. They're just getting bigger, aren't they? Right? So we can cross positive 1 off the list. Let's try negative 1. You see they're just going to keep getting bigger?
Yeah.
So we bring the 4 down. Now what?
Negative 4.
So what's that going to be? 47?
47.
12? All right.
12.
And remainder box?
0.
0. Okay. So we got negative 1 works. How many coefficients? 4. So look at those real quick and just, I'm going to kind of just demonstrate some ways you can sort of think about this. I could look at those coefficients and probably I know I'm gonna get 4 terms, right? Is grouping gonna work?
No.
It's not gonna work, is it? So I've gotta keep going, right? I gotta look for another one. Okay, but at least it's a smaller group of numbers I'm plugging into. What's the first one I should probably try? No, one can't work, right? Because 1's already been crossed off the list. You see that if 1 wasn't a factor of this polynomial, then it can't be a factor of this one, right?
Try 2.
Okay, but we really, before we try 2, we should probably try -1 again, because it could be a double root. And then if it's not, we can cross it off the list. Question?
Wait, why can't you try it again?
Because -1, when this thing gets factored, what this means is that -1 is a factor, right? But couldn't that maybe be a factor? X minus 1 times x minus 1. Right, I mean, it could be, right? See what I'm saying? I mean, x minus 1 squared is just equal to x minus 1 times x minus 1. When this thing gets completely factored, we're just going to have a product of a bunch of factors. But there's no reason I couldn't have the same factor more than once. Right? Remember when we did our graphing of functions? When we graph a function, if we're graphing a polynomial, let's say the polynomial does this. What's unique about that 0 right there? Yeah, it's tangent, and so that's going to be an x-intercept that corresponds to a squared factor, right? Right? Remember that stuff? Okay. So we'd have to check -1 again. It could work again. It could be a double root. In other words, how do we describe that? If something is a root that occurs more than once, then that corresponds to a factor that's taken to a power greater than 1. How do we describe that then? It has a what greater than 1? Starts with an M. Multiplicity. Yeah, it has a multiplicity greater than 1. Okay, so let's try -1 again. We'll change colors, how about? Because we already got 1. Let's try -1. Bring the 4 down. -1 times 4. So what's this going to give us? 23? -23. So that's going to be what? 24? That's not going to work, is it? It's close, but it didn't work. So we can now cross -1 off the list.
On the -1, why
Did I mess that up?
No, the one before. Oh, wait, never mind. It would be.
Because 12 times -1 plus 12. Okay. So let's try, how about 2?
That's not gonna work.
2's going to get bigger, isn't it?
Yeah.
Right? Right, so let's try -2. Did everybody see that? That was good thinking. Do you hear what Elton was saying? Because he looked at that and he said, okay, these are all positive coefficients. And so multiplying by 2 is just going to keep getting bigger, isn't it? Right, so it's got to be a -1, right?
Why didn't the last one work?
Why didn't it work?
How do you know it's not gonna work?
Well, I can tell it's not, I mean, if you just kind of think ahead, because this is where the 0 would have to be. -24 plus 12 is not 0. I just stopped. Okay. So how about this guy, -2? So that's going to give us what? 19. Okay. And then, so it's 19, so we get -38 plus 24.
Wait, 24?
Oops, hang on. I get the wrong. Plus 47, sorry. So that's what, still not going to work, is it?
Ugh.
Right? -38, that's going to be what, 9? Not going to work, right? Everybody agree?
-1 answers?
Say it again?
Why do you use the -1 answers?
What do you mean?
Like those are all the numbers.
Oh, okay, yeah, good question. Okay, Ruby's question is, why did we use the -1 answers? Because when we divide the original polynomial by x plus 1, x minus -1, that's going to give us this other factor. Think about what that, so we could take this original polynomial and we could break it up into x plus 1 times this stuff, right? Times, what's that going to be? 4x cubed plus 27x squared plus 47x plus 12, right? So now I'm just trying to find the factors of that, right? See what I'm saying? So we'll just keep working our way down. That's what I've always called nested synthetic division, right? We can just keep on working down. As the list of coefficients gets smaller, we just keep going, right? So -2 didn't work. -3, how about? So let's see, we're working from this row. So 4, what's next? So 15. So 2. Is that right?
Yeah.
So it's not quite going to work, is it? Okay, let's try -4. 4. So 9, no, what's that? 11. That's going to work, isn't it? Yeah, because I'm going to get -44 and 47 is 3. -3 times, or 4 times -3 is -12 plus 12 is 0, right? Everybody see that? Okay, so then, and that's, now we're in great shape because we found -1 and -4, and what's the size of the remaining polynomial? It's quadratic, right? And do we even really, you can kind of see something else here. The more you do this, do I even have to really write it out? What are the values of A, B, and C? 4, 11, and 3, right? So why not just use the quadratic formula? Did everybody see that? This is A, that's B, and that's C. Get it? Okay, so then the other ones are going to be, what? What's the quadratic formula? -11 plus or minus 11 squared minus 4 times 3. So 4 times 3 is just 48, right? All divided by, so then what's that going to be? 121 minus 48 is going to be 73. Is that right? Oh, is that right? 73? Yeah. So we're going to get -11 plus or minus the square root of 73 over 8. So that's not going to reduce, right? But are those real? Yeah, they're real. They're just not rational, right? They're irrational. But that's fine. We just ask for real solutions. So our solutions are going to be, what was the first one? -1. So we get -1, -4, -11 eighths plus square root of 73 eighths, and -11 eighths minus square root of 73 eighths, right? See how that works?
Do we have to break it up like that?
You could have left it with a common denominator. It's probably not a bad idea to do that though, because then you don't run the risk. What if this had been like a 12? Then, yeah, you see what I'm saying? That would reduce, wouldn't it? Even though this one wouldn't have, that first one would have
We
reduced.
got it wrong, we didn't reduce it.
You wouldn't have got full credit on it. Yeah.
So, so then, you know that there's not any more solutions, because like, so the X value.
Yeah, then we're done. Then we ran out, right? We got it down to quadratic, and so we extracted the last two. And we know from the fundamental theorem of algebra, exactly how many complex solutions does this have? 4. We found them. They're all real. Right? Make sense? Okay. Let's try one where we're looking for, we're going to broaden the search a little bit. So what's the difference in the instructions here? Complex zeros. Okay. So does that really change anything we did? No, not really, right? It all just means that we're going to include i's in our answer. Okay, unfortunately, we can't do, we can't do anything tricky here. We can't solve by or factor by grouping, so we'd have to go back and do the same thing again. Hopefully this will work out quickly. So our coefficients are 3, -8, -2, 12. We have all the factors of 12 over the factors of 3, but we'll just try the, of course, we're just going to try the integers first. So I'll make the list of the integers. Plus or minus 1, plus or minus 2. All we need to get is one of them though, right? Everybody see that? If we get one, why is that all we need? They go in pairs, but then how many are we going to get total? I mean, this is cubic, right? So if I can factor out 1, I'm going to be left with quadratic, and then I can just throw it in the quadratic formula and I'm done. So we just have to find 1 and we're home free, right? So how about if we try 1? What do we get? 3, what's that going to be? -5? Negative, so that's not going to work, is it? All right, we can cross that one out. -1, 3, -11, not going to work, is it? Can you see?
Why don't you just start out with 3 rather than -3?
You'll
'Cause it's-
just drop the first one
Just-
down.
Yeah.
Okay.
2, so it's at -2. It's not going to work, is it? Or is it? -4, yeah, it's going to work. Isn't it? Yeah, it's going to work. 2 times -6 is -12 plus 12 is 0, right? Everybody see that? Okay, so, yes?
What if the little number without an X, I don't know if that you're using the factors of?
Constant?
Yeah. What if it's a prime number?
Then what are the like 7?
Yeah.
You'd rejoice. What are the factors of 7?
Yeah.
1 and 7, that'd be good, huh?
So can we just have prime number problems?
Yeah, like maybe 1 and 1.
1 and 1, that'd make it
I'll
nice,
take
huh?
7 and 13.
7 and 13, okay. It's, it's possible. You have a slight chance of getting one.
So if we just keep
It's fairly random.
Redoing.
until we get it?
Yeah. Uh-huh. Okay, so then 2 works. And then what are the values of A, B, and C? So I could just put those in the quadratic formula, and I'd get what? X equals 2 plus or minus the square root of what? 4. Minus 3 times -6. So this one actually works out not to have i's, right? Let's just pretend for the sake of argument so we can just kind of remember what this looks like. What if that were a +6? Just hypothetically. Then I'd end up with 4 minus 72, 4ac, right? All divided by 6, just hypothetically. And if we did that, we'd get 2 plus or minus, what's that, 68? Is anything going to 68? 4 probably is, right? 4 times 17, yeah. So we get square root of -68. We could turn that into what?
4 times square root of 68, I think 17.
So it breaks into the square root of 4 times the square root of 17. So what's that going to make this when I simplify the radical?
2 times square root of 17.
2 times square root of 17. And what about that negative? Right? All divided by 6. And so now, Ruby, what am I going to do? How am I going to simplify those answers? I've been asking you for a reason. Remember,
You split it?
we split it, right? We're going to split it because we have to split it here. It's not even really a choice because we're going to want to write the answers in the form A plus BI where they're separate terms, right? So we'd end up with, what, 1/3 plus or minus square root of 17 over 3i would be my other 2 answers, right? That make sense? Okay. Only difference being we just got imaginary numbers in there, but big deal. Okay. Okay, how about if we try something like okay, what about this one? We won't even go through the whole thing. These aren't very hard, right? These are really pretty simple. How do I build a polynomial from a list of factors? What's the factor that or for a list of zeros? What's the factor that goes with the 0, -1? X plus 1, right? So this is just going to turn into the product of x plus 1 times what? Okay, here's the part that's a little tricky. Write a polynomial function of least degree that has integer coefficients, right? That has integer coefficients, then what does the irrational root theorem tell us? That if you have an irrational 0, then what about it? Remember? Okay, let me pull that up. Think about it this way. If I have a 0, I'll show it to you, but think about it this way. If I have, this corresponds to the 0, x minus negative the square root of 2. So x plus the square root of 2, right? Well, when I multiply those out, how am I going to get an integer?
If you have the complex conjugate.
Not complex, just the conjugate, right? Think about this. If I were to FOIL this out, or not FOIL, if I were to expand this out, that square root of 2, what's the only way the square root of 2 is going to turn into an integer? I multiply by the square root of 2, right? And how am I going to get that to work? Well, the only way that's going to work is if I multiply by the conjugate of that factor, right? So if the coefficients of the polynomial are integers, then that means that any irrational root has to be part of a conjugate pair. That's the only way that I'm going to get that square root to go away. Look what happens if I multiply those together. What's the result going to be?
Square minus 2.
Yeah, because look, that's a conjugate pattern, right? If I have a plus b times a minus b, then that just equals a squared minus b squared, right? So the only way I'm going to get rid of that radical is if I multiply it by its conjugate, right? And so that is, if we have time, I'll pull it up. That's the irrational root theorem. That's all it really says, is that if you get one of these irrational roots and you have integer coefficients, it has to be part of a conjugate pair, right? Okay. So that's the tricky part of this one. So then what would my answer be? Well, it'd be the product of those 4 things. Now, which two, would it make sense for me to maybe combine those 2 together? None at all, right? Because then I'm battling those radicals the whole time. You always are going to multiply the conjugate pair together to get something simple, right? And then I can just multiply out those 3 in whatever order I want to. Yes, ma'am?
So to plug my answer in, would you use the x squared minus 2 or the x plus the square root of 2?
Well, the answer is going to be, I want to know what the simplified polynomial is, right? So you're going to have to multiply all this stuff out,
Okay.
right? See what I'm saying? But the order to it's you're going to get the same answer regardless. But this would make sense. You can multiply 4 factors in any order you want to, right? But you can only multiply things in pairs, right? So you've got to just kind of pick. Sometimes there'll be a smarter order to multiply them. Whenever you have conjugate pairs, you would always find that product, you know, and then go from there, right? So now it would just be the product of that times that, and you've done stuff like that. That's not a big deal. Okay? How about something like this? Okay, what's the trick on this one, if you call it a trick? Actually, that one's not very tricky at all, is it? What would it, I mean, what would my, I want to find the smallest possible polynomial. What would the factors be?
X plus 5, x squared plus 25.
So we're gonna get, yeah, x plus 5, x minus 5i, x plus 5i, right? Let's do, I gotta pick a little harder one than that. That's not good enough.
Is it gonna be that easy on the test?
What do you do with the eye?
What do you do with the I? Okay.
When you multiply two i's together, it equals -1.
Yeah.
Oh, yeah.
Yeah.
It's the square root of negative what? Then you take it out.
Can we just go back to the shape? That doesn't make more sense.
Okay, let's look at this one instead. Okay, what about this one? So this has to do with the fundamental theorem of algebra. Remember what we talked about? We said complex. We know from the degree of a polynomial tells us the number of complex roots that it has, or zeros, right? They always come in complex conjugate pairs if they're imaginary, right? So then, if negative I is one of the zeros, what's one that goes with that? Yeah, because what is, if I write that in standard form, what is negative I? Written in the form a plus bi. What's a? What's the real part of that? 0. Yeah, so negative I is really just the same thing as saying 0 minus I. So that must get paired with 0 plus I, right? What about 3i? Well, that's the same thing as saying 0 plus 3i. So its conjugate would be 0 minus 3i. Do we write the zeros? No, we don't write them. But they're there, right? Every complex number can be written in that form, right? Remember we said if b is 0, that's a pure real number. What if a is 0? Then it's a pure imaginary number. And if a and b are both non-zero, then it's just a complex number with both parts. Okay? So the point being, if you think of this as being tricky at all, what you'd have to do is you'd have to include I and negative 3i in the mix. And when we generate these factors, the order is definitely going to be important that we multiply them in. So what are the factors going to be that go with these? What should go next? X minus I, right? Then we'll go, what's that one going to be? No, not plus 3i. X minus 3i, and now look how easy those are to multiply together, though. This actually is a pretty easy one. What's the answer going to be here? That's a conjugate pattern, right? So we're going to get first term squared, so x squared minus I squared. But what's I squared? Negative 1. So x squared minus I squared would be x squared minus negative 1. What is that?
Plus 1.
Okay, everybody see that? How about over here? What's this one going to be? X squared, good. X squared minus 9i squared, right? 3i times 3i, right? So what's that going to be? Just expand those out and I'm done. Right? Okay. Last one. This one isn't worth very many points on the test. It's only worth like 7 points.
That would be the answer.
Are you taking a test on this?
Yeah. Yeah.
Yeah, and when you get to pre-calc check, you have to take like this big test.
Are you
See, not taking it.
Okay. So what about this one? Have a look at this one. Yes, sir.
So, because, I'm talking about the last one, because, each one has to have a complex conjugate, does that imply that it is quartic and not, quadratic?
Yeah. Yeah, it has to be. So what's the, answer a couple questions for me about this. So what's going to be the minimum degree of this polynomial?
5 or
It's going to be, there's 3 there, right? So could it be cubic? Hello? Hey, what's up? Who do you need? Oh, yeah, you bet. Okay, bye. Yeah. So there are 3 zeros, so you might think cubic, but that's not it, because there has to be another one, doesn't there? How come?
Because the last one's complex.
Yeah, this one has an imaginary part, right? And so complex numbers with imaginary parts always come in the complex conjugate pairs, right? So if this is, if -1 minus 3i is a 0, or I should say a root, it's not really, it's a root, let's say, then what has to be the other root that goes with it?
3 plus 3.
Yeah, it's got to be the complex conjugate. So that's a minus bi. We'd have to have a plus bi, right? Those have to go together, guaranteed. That's how they always come, complex conjugate pairs. So now we can see that we've got 1, 2, 3, 4 zeros, so it'd be quartic. Could it be more? Sure, we could add more zeros if we want to, but the instructions are to write the I guess I skipped the first part, but it says write the simplest of least degree, right? So we're writing the simplest possible polynomial. So we're not going to add any extra zeros, even though we could, right? And we want integer coefficients and a leading coefficient of 1. So we're not going to make this thing souped up and difficult. We're just going to make it as simple as we can. We're just going to take the product of the zeros that we get, or the factors that we get from these roots, right? So what's going to be, what's the factor that goes with -6? X plus 6. What's the factor that goes with 5? What's the factor that goes with this guy?
Plus 1 minus 2.
Okay, so that's going to be x, same pattern, right? It's just x minus the root. So x minus the quantity -1 minus 3i, right? That's all we do is subtract it from x. And then the last one,
You distribute the negative through.
yeah, we will, right? I'm going to go through one of those. So then we've got x minus the quantity -1 plus 3i. Remember, this is the one where I showed you a little trick that's pretty helpful. So let's deal with the red ones first because they're conjugates, right? To make this easier, the best thing you can do here is if you, whenever you have something like this, is distribute the negative sign. And what's that give us? And that's going to give us x
Plus 1 plus 3i
x plus 1
plus
plus 3i times x plus 1 minus 3i. Okay, doesn't that look better? Because I can do this. And now those look like conjugate pairs, don't they? I've got a plus bi and a minus bi. See that? So then what's the product going to be? If I do a product of conjugates, I just get a squared minus b squared, right? So then this whole thing would just end up being x plus 1 squared minus 9i squared. Do you see that?
9.
So, right? What's 9i squared? Minus 9. So minus -9 is plus 9. And that's no big deal, right? If you do it that way, it's pretty simple. What's x plus 1 squared? Quantity squared? X squared plus 2x plus 1, but let's add the 9 also. So there you go, right? That's what all this stuff boils down to, is just x squared plus 2x plus 10. And then out front, I've got this stuff. But that's just a matter of expanding some things out, right? Okay, make sense? All right, finish those suckers up. Those assignments, those 7-1 and 7-2 assignments.
Wait, well, we're adding. Oh,
Yeah.
wait, we have another test for you? No, it's not yet. Like, so we have 4 tests?
Yeah, from module 7, you'll have or from unit 3, you'll have a total of 4. You've done 3, and then this is the last one.
I've done 2.
Oh, okay. Theoretically, you've done 3. Yeah.
Wait, so how many tests are gonna be over this?
Just one over this stuff.
How
Yeah.
long will it be, like?
Right now, it's set at I think 6 questions, but I might even make it 5. I mean, just
They take a little while.
I know they do. That's what I'm thinking as I go through this too.